Right. So our next topic is Rutherford scattering equation. Okay. So here an alpha particle is projected onto a nucleus, gold foil, gold nucleus, and we will be studying the scattering cross section of this activity. Okay. So here let's say N is a nucleus, and a particle is incidenting with velocity p naught. V naught is the initial velocity of the alpha particle, and the particle will take a hyperbolic path. If it incidents at oblique angles, and if it incidents head on, it will simply go back. Okay. So we have to study this phenomena. So now let's say, so this is the incident direction of the particle, and this is the emergent direction of the particle. Then the angle of scattering, where should we measure? The angle between incident ray and emergent ray. So to measure the angle, we have to consider either a converging pair or a diverging pair of vectors. So this is the incident ray and this is the emergent ray. So at this point, where should we measure the angle? I mean, if you count here, one is incident ray, another is emergent ray. So either you have to extend this one further or this one backwards, so that you should get either a diverging pair or a converging pair. This is the angle of deflection or a scattering angle. Okay. So now we consider the symmetrical elements in this situation. I'm defining a parameter called P. P is the impact parameter. Impact parameter means the perpendicular distance between nucleus and the incident particle. So considering the incident direction, it is traveling along this ray, along this direction. So the perpendicular distance is called impact parameter. So that is the closest distance that a particle can approach. I mean, there is a in the case of head-on collision. So let's say we're starting with the same initial velocity v0. This is the nucleus, and this distance is called v. So when the particle incidents head-on to the nucleus, it will simply revert back. It takes a 180 degrees reverse track and travels along the incident direction, opposite direction. Okay. So the least distance between the nucleus and incident particle is called, I'm marking it as B. So in this case P is 0. So now taking the distance between these two nuclei. As D. Right, now we will apply the conservation laws for this situation. So since there is no external forces involved in the story, we can apply conservation of momentum. So in the first case, conservation of momentum, at point A and at point C. So this is point A. This is point C and this is point B. So M naught P is equal to MVT. So D is the distance between nucleus to point C. So the actual track of the particle is, it starts from A, approaches up to point C and reverts back and takes a track to C. Okay. So what are we doing? Okay, so here, I mean, which conservation law should we apply is a matter of discussion. So, is the potential, I mean, we have to consider the nature of the potential. The potential is spherically symmetric. So, at a fixed distance from the nucleus, the force experienced by the particle is constant. So, it is called isotropy in space. So when you have isotropy in space, that means the energy is constant at a fixed distance from the point. Then we have to apply conservation of angular momentum. Right. So isotropy in space leads to conservation of angular momentum. So I am applying the conservation of angular momentum at point A and at point C. So this is at A. This is at C. Okay. So in this story, what we know is V naught is known. What is the initial velocity of the particle, and mass of the particle is known. And based on the initial orientation of the particle, incident angle of the particle, we can predict the value of P. So these are the three known parameters. M is known. D is unknown, V is unknown. I mean, we cannot stop the particle on the midway and confirm where is it stopping and how far is it from the nucleus. So these two are unknown variables. V naught P, these three are the known variables. V and D are unknown. Okay, so that is one equation. So this is a conservation of angular momentum. This is because isotropy in space, central potential. Central potential is isotropic in space, so we can use conservation of angular momentum. And the parameters known to us are these three. These two are unknowns. So now, conservation of energy. Half mv naught square. So by the time it reaches point C, sorry, the potential energy is 0 at point A. we are assuming it is very far from the nucleus, so there is no potential energy involved there. Particle has only kinetic energy. So on the other end we have half mv square plus, since this is alpha particle, Ze times 2e by 4 pi epsilon naught d. That is the potential energy at point C. Okay. So these are the two equations from case 1, and from case 2 we have to go for conservation of energy again. Because in this case there is no kinetic energy, so all we get is only the initial kinetic energy will be balanced with the potential energy at point B, whatever that point. So I call this as C prime. Okay, so these are the three equations that we come across. So now what are the known variables here? Jd, 2e, 4 pi epsilon naught, all are known. M v naught square is known. B can be calculated probably. Right? B can be measured. So these are all known things. M is known, v naught is known, Jd, 2e, 4 pi epsilon naught, B. So here V and D are unknowns, so it is better to avoid those two. Okay, so we try to eliminate them, otherwise at least this V should be avoided, because somehow D also can be measured by seeing the experimental observations. So I am trying to eliminate that V. So what do you get? V is equal to V naught P by D. So that is one equation. Then what all we need to do? So how many equations do we have and how many variables? We got 3 equations and number of variables. So this Jd, 2e, 4 pi, epsilon naught, all these are constants. What are the variables? M is also a constant. V naught may be a variable, and this V should be avoided, B and D. So how many things are there? V, V naught, B, P, D. Rest are constants. What are the things? M, Jd, 2e, 4 pi, epsilon naught, all those are constants. So these are all constants, and we have 5 variables, and we got 3 equations. So what can we do? At most we can eliminate 3 variables. So any 3 can be avoided, and the rest of the 2 becomes dependent. Okay. So I try to avoid these velocity terms v and v naught. First of all, I have eliminated v from here. So I obtained v and substitute wherever I find v. Okay. So what do you get? So half m v naught square is equal to half m v square means v naught square p square by d square plus z square 2z square by 4 pi epsilon naught d. And half m naught square is, from this equation we have half m naught square is equal to 2z square by 4 pi epsilon naught b. So I'll replace half m naught square everywhere. So I substitute this. So what do I get? 2z square by 4 pi epsilon naught d is equal to 2z square by 4 pi epsilon naught d p square by d square plus 2z square by 4 pi epsilon naught d. So I'm replacing half m naught square. So in total, what do you get? 1 by b is equal to p square by bd square plus 1 by d. So which one should we avoid? So we'll try to pick the term from the second study. So I'll try to separate b. I'll try to get the value of b. So what is this? bd square p square plus bd. So multiplying with bd on both sides here. So in total, I can cancel this. P square plus bd is equal to d square. So I need to get the value of b. So b is equal to p square minus d square by d. Okay. So that is how I related the parameters defined in the two studies. So the parameters defined in first study are p and d, and the second study it is b. So I got a relation between b and pd. So it is d square minus p square. So in total we have 5 variables here and 3 equations. So we can eliminate 3 and 2 variables will remain in floating. Still their values to be fixed. So here we have eliminated V and V naught and fix the value of P. Still D and P are in floating. We need to get those two values, or we need to generate at least 2 more equations to eliminate those two, if at all. Okay, so I'm considering trying to generate 2 more equations related to that. So here I'm considering this distance from the center of the parabola. Every point on the parabola will be at equal distance. So this point is also actually on the line. So from the center of the parabola, hyperbola. From the center of the hyperbola, every point on the hyperbola will be at equal distance. So if this distance is A, let's say I call this as O. If OC is equal to A, then OP, what is that? What did we mark? We call it as M. So OP is equal to OM is equal to A. OC is equal to OM is equal to A. So, from the center, every point on the hyperbola will be at equal distance. So now we need to get the values of this P and D in terms of that, in terms of A. We need to get the value of P and D. Okay. So what is P? Let's say this angle is theta. This angle is theta. Then what is that? P is equal to Mn. So let's say if you write tan theta, opposite side, Mn by Mo. P is 8. Okay. Yes, then I need to get the value of D. What is D there? ON plus OC. So I have to get the value of ON. I can write it as, let's say, what is cos theta? It is A by cos theta plus A. What is cos theta from this triangle? OMN. A by ON. So ON is equal to A by cos theta. So in total D is equal to A times 1 plus secant theta. So we get the value of P as well as D. Okay, and we can substitute it there in that equation. So b is equal to d square minus p square by d. D square is a square 1 plus secant theta whole square minus p square a square tan square theta by d a into 1 plus secant theta. So what do you know? 1 plus tan square theta is equal to secant square theta. You can use that and simplify that equation. So here you get 1 plus secant square theta plus 2 secant theta. So what you get is a square times 1 plus secant square theta plus 2 secant theta minus a square times tan square theta can be written as secant square theta minus 1. Secant square theta minus 1. So this secant square theta gets cancelled. By a times 1 plus secant theta. So in total you will get 2a. So here you got 2a square secant theta and a square plus a square, 2a square. So if you take 2a square in common, you will be left with 1 plus secant theta. So result is 2a. Here I am defining eccentricity as ON by OC. Distance to the nucleus by distance to the hyperbola is the eccentricity. So that is given by so ON is ON is what? ON is a by cos theta. So a by cos theta by a, which is secant theta. So eccentricity is secant theta. So now we can replace that secant theta wherever. So from here P is equal to a tan theta, that is a times square root of 1 plus 1 minus secant square theta. Is it? So for hyperbola epsilon is greater than 1. Okay, so P is that. Then other term D is equal to A times 1 plus secant theta. A times 1 plus x. What about D? B is equal to 2a. can write in terms of P if you want. 2 times P cot. And that theta also can be written in terms of phi's if you want. So what is the relation between theta and phi? 2 theta plus phi is equal to 180 degrees. So theta is 180 minus 5 by 2, 90 minus 5 by 2. So B is equal to 2P part 90 minus 5 by 2, which is 2P tan 5 by 2. So you can replace, so from this A is equal to P tan 5 by 2. So wherever you have A, you can write in terms of 5 by 2's. So P is equal to, so that cannot be done. A is equal to P tan 5 by 2. That's all. So D is equal to, what is D then? A into 1 plus epsilon. Which is B by 2, 1 plus epsilon. So using this, what do you get for epsilon? Epsilon is equal to secant theta. So 1 by cos 90 minus 5 by 2. Because 90 minus theta, sin theta. So in total we have, initially we got 3 equations and 5 variables. So we got 2 floating variables and 1 fixed variable. And to fix these 2 values, we introduced another pair of terms, theta and A. So 2 new variables are introduced. So even if you try to eliminate them, these 2 will remain. So entire all these terms can be written in terms of A and theta. All B, P and D values can be written in terms of A and theta. And further we have introduced another term, eccentricity E, which links with theta. So either we can write A in terms of eccentricity or theta in terms of eccentricity. I mean, we can eliminate one more thing from there. So eccentricity is actually theta, linked with theta. So we can eliminate theta. And finally, we can write theta in terms of scattering angle phi. So in total, here are the 5 variables. We are left with 2 floating and 1 fixed variable. And in the next course of action, we are introducing 2 more variables, A and theta can be replaced with phi somewhere. So A and phi. And another term, eccentricity E. Right? So in total, you can write either A in terms of P. So how many variables will be left with then? V, V naught, B, P, D. Here A, theta, phi. So out of this one can be eliminated. So you will be left with A and phi. So still one variable is floating. So instead of P and D, you can write A and phi, that's all. That's all you are left with. So you'll have relations between A, P and phi. Otherwise B, P and phi. Then D, P and phi. So you can replace any two with the other two. So in total you can get the relations for B, P, D in terms of A and phi. Otherwise eccentricity and phi. That's all. And scattering cross section calculation we'll see in the next session.